Good evening. Welcome to our session for 2601. So thank you for bearing with us. Happy to announce that we are no longer going to be having the same problems with the chatting as before. So we should be on at the scheduled time unless otherwise communicated for some other reason that will not be related to the chatting. Right. Last time we were discussing recursive definitions, right? We were discussing recursive definitions, and I think we were answering to the question odd not AB, right? This was the question that we're answering to. There we go. And we had our proposed solution here. Right, I want us to go and have a look at the one that is in the assignment, right? So let me put it there for you to see, so that you can see how we did it. So it's odd not AB, appropriate universal set, generators. We give the generators, then we give the function, then we give the or how we generate other ways that are in the function, right? So a copy of this will be sent to you as well, so that you can have a look and compare with your solutions for the assignment as well. Right, now let's switch back to the business of today. We want to look at proof by induction. Now, proof by induction simply states that if a subset of a universal set contains the element n and is such that it contains k plus n whenever it contains k, right, then that subset is in fact equal to the universal set. Right, so let's break this down in terms of recursive definitions. A subset of a universal set, right, we're saying even if say odd not AB is a subset of a universal set. So we're saying a subset of a universal set contains the element n. So we now have n is an element of odd not AB, for example, right? And is such that if it contains k plus n whenever it contains k, so here we're saying if k is an element of odd not AB, then k plus n is also an element of odd not AB, right? So if k is an element, then k plus n is also an element. If we have a subset that behaves in such a manner, then that subset is in fact equal to the universal set, right? So now let's try and put that into practice, right? So we see how this induction principle is in fact a recursive definition. Right now, so you need to recall this statement because in the exam for 1 mark, they ask you to give the principle of induction. Right, so you can recall it in any or in your own words, in a way that you can understand. Right, so how does this principle of induction work? Let's say we have such a question, right? Can we claim that for every n is an element of positive integers, 1 plus 2 plus so and so up until n is equals to n multiplied by n plus 1 over 2? Can we make this claim? So let's see if we can prove this by induction. Induction says if we have a subset of a universal set, so let's say our universal set is Z plus, so let's say A is a subset of Z plus, right? And N is an element of that, so we need to give 1 is an element of Z plus. So we've given an element, right? Now let's check that 1 is an element of, sorry, here we're supposed to say it's an element of A. and 1 is an element of the subset. We want to check if 1 is an element of A. On the left-hand side, we have got 1 is the first element. On the right-hand side, we have got 1 multiplied by 1 plus 1 all over 2. This is equals to 2 over 2, which is equals to 1. Right, so since the left-hand side is equal to the right-hand side, 1 is therefore an element of A. Now, we've proved that 1 is an element of A. Now we want to check, does the relationship hold? So let's assume an arbitrary element K is an element of A. What does that mean? It means that 1 plus 2 plus 3 plus so and so plus K, right? We're substituting K for N, is equals to K multiplied by K plus 1 all over 2, right? This would mean that K is an element of A, right? If we prove that K plus 1 is an element of A will then become equal to Z plus. So what do we mean by this 1 plus 2 plus 3 plus and so forth plus K plus 1. So K plus 1 comes after K is equals to, so if you substitute K with K plus 1, we've got K plus 1. We've got K plus 1 all over 2, right? So this can be simplified to K plus 1, K plus 2 all over 2. But if you manage to prove this, then A is in fact equal to P. That is, the formula or the equation under test holds under all positive integers. So let's see how we prove that. The left-hand side is equals to 1 plus 2 plus 3 plus and so forth up until K plus K plus 1. Okay? But we have also established that by this assumption that 1 plus 2 plus 3 up until K is equals to K plus 1 over 2, which means we can then substitute this part with K plus 1 all over 2, right? Then we continue with plus K plus 1. Right. If we simplify this further, we then have common base 2 into 2, 1 multiplied by this, we've got K plus 1 plus 1 into 2, we've got 2 K plus 1. Then we further simplify, we have K plus 1 is common here, we factor it out, K plus 1, then we remain with K plus 2 all over 2. And this is equal to right-hand side. Okay? So now the conclusion that we draw is the following, right? Since K plus 1 is an element of A whenever K is an element of A is therefore equal to Z plus, and the equation 1 plus 2 plus 3 plus N is equals to N plus 1 over 2 holds for all positive integers, right? That is Z plus. So we have proved that the given, if you go up a little bit, the question was, can we claim for every positive integer that this holds? The answer was that since k plus 1 is an element of k whenever is an element of A, whenever k is an element of A, it means that our subset that we initially said is a subset of all positive integers is actually equal to the set of all positive integers. Meaning, if our subset contains only elements that made that statement true, we are saying if k plus 1 is an element whenever k is an element, we're saying this universal set makes it true. The universal set is in fact equal to the subset, meaning that it is in fact true. Right. Any questions? No, we did it, especially on the last proof part. That is where most of the questions come through. Questions so far? No? All right. So let's move on to the next question. Prove by induction that n squared is greater than 2n 2n plus 1 for all n is greater than or equal to 3. So again, we want to have a subset. Assume A is a subset of let's call this, so the universal set is n is greater than 3, right? So let's call this n is a subset of all positive numbers greater than 3. So let's call this set Z3 plus, right? N is a subset of Z3 plus, right? And 3 is an element of A. 3 is the smallest number that is applicable, which is n is greater than or equal to 3. So 3 is the smallest number. So we want to prove 3 is an element of A, right? So to prove that, we have the left-hand side equal to, so let's do this. Left-hand side is equals to 3 squared, which is equals to 9. Right-hand side is equals to 2 multiplied by 3 plus 1, which is equals to 7. Right? Here we have left-hand side is greater than right-hand side. Therefore, 9 is greater than 7. Therefore, 3 is an element of A. Now, next, we need to assume K is an element of A, an arbitrary constant, right? So that is K squared is greater than 2K plus 1. And after this assumption, we need to prove that K plus 1 is an element of A. That is K plus 1 squared is greater than 2K plus 1 plus 1. Or you can write it as 2K plus 3, right? So this can be written as an aside, okay? This is not part of the solution. I'm saying this can be rewritten as that. Right. So in order to do our proof, left-hand side is equals to K plus 1 squared. Right. We can expand this, right? And have K squared plus 2K plus 1, right? If we expand it to say K squared plus 2K plus 1, okay, what then do we get? Right, we know 2K plus 1 is less than K squared. 2k plus 1 is less than k squared, or k squared is greater than 2k plus 1, okay? And we'll see that here if we've got, we can have 2k plus 1 plus 2, okay? So this one over here, if we replace k squared with 2k plus 1, we've got 2k plus 1. This was k squared before, plus 2k plus 1. This is greater than that, right? By virtue of k squared being greater than 2k plus 1. If we substitute k squared with 2k plus 1, then this becomes less than that according to the initial assumption, right? So now we know, we now have this is equivalent to 4k plus 4k plus 2. Right? This is equivalent to 4k plus 2. So we want it to be, so we have, rather, let's put it as, this is equals to 2k plus 2k, right, plus 2, right? But we know, but 2k is greater than 1, right? 2k is greater than this one. So 2k is greater than 1 since A, or element of A, right? Since n is greater than or equal to 3. So 2k is to be greater than 1. So if we have that, therefore this is greater than 2k plus 1. 2k plus 1 plus 2, which is equal to the right hand side. Right. Is there any questions then on how I have managed to, or I'm doing this? Questions? So you can either raise your hand, use the Q&A, or the chat option. No questions? All right, now let's look at the assignment question. Assignment 2, that is, we're talking about. All right. So they said, give a recursive definition of the set P of all positive integers greater than 0. So the recursive definition, we said 1 is an element of P. If X is an element of P, then X plus 1 is an element of P. Nothing else is an element of P. We've defined all positive integers greater than 0. Right. Then next, formulate the appropriate induction principle. So the appropriate induction principle would be to say, in this case, if a subset of P contains 1 and also contains K plus 1 whenever it contains P, then the subset is in fact equal to the inverse set, which in this case is P. Right, and then part 3 then says, use mathematical induction to prove that that sequence is equals to 2n squared plus 9n for all positive integers greater than 0. Right, first we said assume A is a subset of P and 1 is an element of A, right? Then next we say prove 1 is an element of A. Then we said if we put 1 in 4n, 4 times 1 plus 7 gives us 11. And then right hand side, 2 times 1 gives us 2, plus 9 gives us 11. Therefore, since the left hand side is equal to the right hand side, 1 is an element of A. Now we assume K is an element of A, that is, If we substitute in for k, we get that 11 plus 15 plus 19 plus and so forth, plus 4k plus 7 is equals to 2k squared plus 9k. Then we want to prove that k plus 1 is an element of A. That is, if we add one more element, we still maintain that. So we've got 4k plus 7 plus, right, and this is what I'm talking about, plus, so 4k plus 7 ends here. The next one, the k plus 1 comes in here. 4k plus 1 plus 7 is equal to, now we substitute where there was k with k plus 1, 2k plus 1 squared plus 9k plus 1, which when simplified becomes 2k squared plus 13k plus 11. Right, now the left-hand side is equals to all of that, but we know that this part is equals to 2k squared plus 9k, which you see being replaced over here. And we have got the 4k plus 1 like this. So if we simplify this, we are going to have 2k squared, which is there. We're also going to have 9k, which is this one, plus the 4k that comes from here, plus 4 plus 7 that was sitting here. So this is equal to 2k squared plus 13k plus 11, which is equal to the right-hand side. And since the left-hand side is equal to the right-hand side, it therefore shows that k plus 1 is an element of A. For all k is an element of A, and this proves that A is in fact a subset of P, and that is the equation holds for all integers greater than 0. Right. It holds for all integers greater than 0. Cool. Any questions? So at where we are sitting, right, if you go and look at any past paper, you are now able to do question 1 to 3, which will constitute of 30% of your exam. So far we've managed to discuss up to 30% of the exam. Right, so feel free to already start going and attempting those questions and sending them attempted solutions so that you are caught up with where we are and where we're going. Right. So the next topic for discussion will be regular expressions, and I think that's chapter 4 or chapter 5 in the textbook. So that will explain to us another 10% in the exam, and in total we'll now have 40% complete. Right. So I'll wait for your questions, and if there are no questions, that will be it for today. Then starting on Thursday, we'll be moving this class to 6:30. We'll be moving this class to the 6:30 slot, right? So there will be an alteration on the timetable. Please make note of that. An email will be sent to that regard as well. Right. Thank you very much for attending. Enjoy the rest of your evening, and from me to you, I say good night.